Great. All right. Awesome. Well, welcome everyone to the next Northwest Database Society Symposium. We're very happy to have with us today Professor Kurt Stockinger, who's visiting us from the University of Zurich. So Kurt is both a visiting scholar here in the Allen School for the rest of this academic year. And at the University of Zurich, he is of course, the professor of computer science, but also the director of studies in data science and head of the Intelligent Information Systems Group. He's also an external lecturer, and his research focuses on data science with emphasis on big data, natural language query processing, query optimization, and even quantum computing. So essentially, his research interests are at the intersection of databases, natural language processing, and machine learning. So welcome.
Thank you, everyone. It's a pleasure to talk here in Seattle. My talk is about querying databases in natural language, and natural language is what we typically speak. And the first question is always, how do you pronounce your name? Martha just asked me about my last name. I thought that's complicated. I start with the first name. So this is every time when I go to Starbucks, they ask me my name. They don't really know what to do, but then I say, there's a gentleman called Kurt Cobain. The younger people might not know. The older ones know he's from Nirvana. Nirvana was founded in the Seattle area. That's his house. So this is he's the other. So you would say Kurt. Yeah? That's not exactly how my name is pronounced. If you want to know really how it is pronounced, then oops, I see something else here. There's a little delay. Yeah. Then there is a song called Hier kommt Kurt. It's by Frank Zander. If you have some time in the afternoon and the evening, you can listen to it. The song is not so good, but I like this. At least I have a song now for my name. It's a German song. It's almost close. But if you want to know really how to pronounce my name, the one who can do it best is this gentleman here, Arnold Schwarzenegger. He was the governor from California, also a bodybuilder. He's from my country, so if you want to know how to pronounce it, ask him. So it's cool. Okay? We look very similar. I don't know. So
he's Austrian, he's not Swiss.
Exactly, yeah. So I'm still Austrian. I become Swiss, hopefully in the next few weeks. We will see.
Let's get rid of the top thing. Hold on just a second. Get rid of this.
So next thing is also a bit complicated. Where's my university located? It's Zurich University of Applied Sciences. It has a funny German expression, ZHW, Zürcher Hochschule für angewandte Wissenschaften. Where is it? It's in Switzerland. Switzerland is here in the center of Europe. Here are the nice Alps. Then you have been in Zurich just recently, right? So you know where it is. So this is, you have seen maybe the Swiss flag. Here in the US, the Swiss flag is often used for actually the Red Cross, but it actually should be the other way around. So here's Switzerland, here's the university. What is special here? So we are University of Applied Sciences. This means we do a lot of applied research projects with industrial partners. So this means we're not so theoretical. We like theory, but we like theory and also turning it into real world problems. Our most famous lecturer, we are proud of it. It's this gentleman. Maybe you've heard about him, Albert Einstein. He was there a few years ago. He didn't stay too long. Maybe our standards were too high, or we didn't realize the potential of him. Afterwards, he went to Bern, which is like an hour from Zurich. He worked in the patent office and did something cool, but it all started at our university. Good. So let's see what we're talking today. So I have prepared 3 different questions: how to actually build systems that can, how to query databases in natural language. How well do these perform in the real world? As I said, I come from a very applied science research, so I want to see how things really work. And then what are also the challenges for additional research? And for those people who are still around, since I will be around here in Seattle and for the next 6 months, I have 2 more topics, so just 2 slides. One is about quantum computing and one about query optimization. So if we have 6 months to discuss it also then. Okay, good. So let's jump into the problem of how to query a database in natural language. Okay, here's a very simple database. Basically, just have 2 tables. We have countries and we have institutions. and there can be several institutions in a country. So a one-to-n relationship, trivial. Now the question that we want to answer is, find all the institutions that are located in Italy. Remember, Switzerland is just ahead of Italy. And it's also between France. So how do we do it? So basically you ask the question, then you see this is a SQL statement. You need the table institutions, you need the table countries, you need to do the join right, you need to do the join conditions, and you need to choose the right things. It's a simple database, you can all do this, okay? But how do you do it? How do we do it so that you don't have to write SQL? That you do it in natural language, okay? And here comes the first interesting thing is, why is it hard to do natural language processing? If we all, sometimes I even tell to my wife, she speaks Brazilian Portuguese, and we speak at home German and English and Portuguese. And there's always misunderstanding. And sometimes I say, why don't we talk in SQL? We would be much more accurate than just this language. I mean, just this simple question. How many great people come from Zurich? Simple, no? Then you know it, you have been there and you have met many people, you didn't meet me, so I disqualify here. So first question is Zurich. What is meant by Zurich? Zurich is this beautiful city here on the lake. In the background, you see the mountains. They're kind of similar to the mountains that we see here, or that we saw here a few hours ago when there was still sunshine. Or do you mean the canton of Zurich? Canton is basically like a state, like the Washington state. Here's Zurich. Tina Turner used to live here, you know, the Swiss singer, Tina Turner, who also became Swiss at some point. Or do you mean the Zurich Insurance Company? That's one of the leading insurance companies in the world. It's just sitting here nicely on the Lake Zurich, you see. Nice building from the 19th century. So what do you mean? Zurich, one of these three. You have three choices. There's even another question here. How many great people are from Zurich? What do you mean by great? Is it the size? And then is it meters? Is it inches? Is it whatever? Or do you mean great the achievement? Is it tall or whatever? So even this small thing, I have already so many questions that are completely ambiguous, non-well-defined. Okay, if I do it in SQL, maybe it's much easier. So the question is, how do we tackle it? And here, the thing, what we tried in 2012, this is some time ago, when I was still working in a bank, Donald Kostman, who is now at Microsoft, was then at ETH, and we said, how can we solve it? And we did a very simple approach, and it worked actually extremely well. So since I worked in the bank at this time, we had the use case. This was inspired by a real world problem in the bank. There was Lehman Brothers just fell, a financial crisis, and we want to see how can we query our huge data warehouse. We had terabyte data warehouse. And take this question, find the top 10 customers with securities of bank A and rank them by trading volume. That's the question. How do we turn it into a SQL statement without knowing the SQL, okay? So what we did at this time, and this was 2012, we said, we only do keyword search. We don't do natural language processing. Natural language processing is too hard. But basically the idea that we just had two tricks. One trick is, and we were inspired by combining database technology with information retrieval. So the trick was, let's build an inverted index over the whole database. Just one big, assume the database is a document store, okay? Like you can index the internet, so why can't you just index also a database? One inverted index, and the second one basically on the schema. So all the tables, all the columns and on. So basically we had these two main data structures. And with this one, we could answer the question quite easily. So what we said, go through all these things here that we have in our question. If we find it somewhere in our values, so this is our big index that we had, it's good. Or if we find it somewhere in our schema, it's also good. So the schema we call the business objects, and the values is basically what we have. So then what we did here, we went through the question and we said, find A, we don't understand. Top is an operator. 10 is a value because we have a value somewhere in the database. Customer, we know because there is a database table that is called customer. Securities, we have a database table called securities. Bank A is somewhere in the data and so on. Rank, we have. And then basically we just combined it. So we had a set of tables. And the nice thing is that we had then is, if some tables are related, so semantically similar, there's a primary foreign key relationship in between. And this one you could use, and it worked quite well. Okay.
We don't need LLMs.
Wait a bit. At this time, no one knew what an LLM is. And we didn't even know what AI is. Now, 9 years afterwards, we said, okay, this was the time this was 2021, when suddenly transformers came out. And there was this famous papers, all you need is attention. And then what we said, can we not treat the problem as a machine translation problem? So at this time, I worked with a natural language processing guy who translated French to German or to English or to Romanian or to Polish, whatever. Why can't we use the same approach also for translating natural language to a database query language? At the end, it's all a language. And what we did is what we say, okay, take a neural network architecture, then the transformer models, and see how we can use them for solving the problem. So what we did, we said we need a question, our natural language question. We need the database schema, the tables, the columns, the relationships, primary foreign key information, and also the database content. And what we said, let's put all this information do some pre-processing, then we do encoder and decoder, that's the traditional neural network architecture, then translate not directly into SQL, but let's translate something in between. SAMQL is a semantic query language. It's an abstract syntax tree, basically. So rather than a specific database language, do it a bit more abstract. Because then you can translate it afterwards to SQL, to Sparkle, to your own database language or any query language, and then execute it, okay? So this is the basic idea. How does it work? Here you see again the question that we originally had, find all the institutions located in Italy. Here we see the SQL statement. And basically here we see how we process it. So here's the natural language question, find all the institutions located in Italy. And here's basically the database schema, the whole database schema plus the database content. Then we encode it, basically we put it into a vector. The E stands for embedding. Then we put this huge vector that we use when we encode our question and the database schema. We put it into the neural network. And then the output is a specific encoding. And the arrows that you see here, this is the attention. So basically from these transformer networks, what attention basically means, learn the correlations between your natural language questions and basically the database tables, the columns, and the database values. So for instance, we find out that institution is correlated with the institution. So in my natural language, I have institution, and I have a table also called institution. So here, this is an attention which is learned by the neural network. On the other hand, the institution is also correlated or learned. There's a database table called institution, the name. In this case, you basically see how it learned. If you don't have institution directly, but say a company, then you might see that between a name in the question and in the table, you also have learned this. So this is the basic idea. So this is the encoder, okay? Now it's encoded, but now you need to, basically now the neural network has understood there's some questions, how a specific keyword is related to a table or a column. Now we need to translate it back into a SQL statement. And how do we do it? We use the intermediate query language SAMQL and also a grammar. So once you have a grammar, you can translate it better. So this is now a deterministic approach. And the grammar basically says there is a root, and there is a select, and there is a filter. And if you continue, the select, for instance, in this case, A means there's no aggregation, but you need a table, the institution, and the institution name, and no aggregation, there's a country, a name, and then the value. Okay, so like by this, you use the intermediate grammar and translate it, and the problem is solved. Okay. The question is, how well does it work, and how can you evaluate how good it actually is? And there's a famous benchmark in the text to SQL community is called the spider benchmark. Yeah.
Question. So could you look to the last slide?
Mm-hmm.
So I wonder if it's guaranteed that the query that it will generate is always valid, or you need to do some validation afterwards.
So in this case, it's a grammar. The SQL statement is generated is always true, or it's semantically it's correct. or let's say syntactically is correct, whether it's semantically correct, that's another question. And this depends on how well the system has actually learned it. Mm-hmm. So that's the advantage if you have a grammar in the back, because then you always assure that at least the syntax is correct. We're currently doing this also with Sparkle, where we don't have a grammar. And sometimes the output, even with the best neural networks now, they just produce kind of Sparkle, but not syntactically correct one. Okay. So now, and again, this is 2001 now. And at the time when we published this, of course, you can only always publish this if you have the best. So we had at this time the best system out there. How was it evaluated? On the spider dataset that I said before. And what this contains is 200 different databases. Each one of them has about 5 tables. So it's a pretty small database, but you have 10,000 or more than 10,000 natural language SQL pairs. So this is the thing you can use. About 8,700 are used for training and about 1,300 are used for evaluation. So basically train it, wait a few hours or days or weeks, and then validation means evaluate how well it performs. So you have a gold standard and you check whether what you generated is the SQL query that they expect or the answer from the SQL query. So now if we look, where is the world now? And as I said, this is the spider benchmark. This is currently the arms race between the database guys, and mostly actually, even though it's a core database problem, most of the people who are in there are from the NLP community. Within this benchmark, you could see I saw 2 systems are actually from Seattle. One of them is even University of Washington, and I figured out that Luke Zottelmeuer, he's even 1 floor above me. I even saw it quickly this morning. I didn't even know that this paper was. But where are we now? And if we look now, best system, 91.2% accuracy. 100% accuracy is you've completely fulfilled the task. 91.2, when we did it 3 years ago, it was like 60%. And now it's already 90%. And I remember last year in Vancouver, there was a podium discussion about NLP and databases. And someone said on the podium, yeah, text to SQL is a solved problem. And if you look at it, you see, yeah, it's a solved problem. 91.
A quick question. So when they do validation, do they check the correctness of the query or of the answers?
So there are 2 evaluation methods you can do. And the funny thing is how it was in the beginning is they check the SQL statement, and there is in natural language processing, there's something which is called a blue score. So you have a gold SQL query, then they generated one, and then they checked with a blue score whether the SQL statement corresponds to the original one. It's not a good measure. A better one is then they figured out it's better to execute the query, look at the result, and then compare the results. So there are at least these 2 measures. A third one is even a more strict one. So if we look at it, we think it's, so the question is it really a solved problem? If it was a solved problem, and on page 41, my talk would be finished and I could go home. Luckily, and there's the big answer is no, it's not a. In academic settings, it's maybe, and if you're small toy data sets, what I might call, then it's maybe solved, but in the real world, it isn't. Okay, and this is basically now the second part of the talk. How do these systems perform in the real world? Okay. By the way, the soda systems that we developed 9 years ago, we developed it on a real world database. We had like in the Credit Suisse data warehouse that we used, we had 500 tables, and it worked already quite well. But of course, not 100%. So now let's see where we are now. This is a picture from a spiral galaxy that's here's most probably a little black hole in there. Magda, I remember you worked on the astrophysics dataset, SDSS, Sloan Digital Sky Survey. This is some data from the Sloan Digital Sky Survey. And why is it interesting? Why astrophysics? They have massive, first of all, they have massive amount of galaxies. And they want to study basically the sky, how it looks like, where do we come from, and so on. So basically, this is the biggest thing we have on our universe. And they store a lot of data in relational database, luckily, thanks to Jim Gray, who convinced the astrophysicists to store data in relational databases. Many other scientists still don't do it, but at least astrophysics is ahead. On the other hand, if we go from a macrocosm now to the micro, do you have any idea what this could be? This is a cell, exactly. And there this strange thing going over the cell.
Germs.
Say it again?
Is it like the virus or germs?
Exactly. And this is a cancer. Basically, this is a cancer cell. And why is cancer interesting? There is the Swiss Bioinformatics Institute in Lausanne, so close to Geneva, and they produced also a lot of bioinformatics databases. And they also store a lot of data. They have, this is about cancer biomarkers, so the goal is here how to find out which specific indicators in the body kind of indicate that there's a cancer and how you can treat it. Okay, why is this important? The human genome has about 50,000 genes and 3 million base pairs. And bioinformatics is also known as one of, next to astrophysics and high energy physics, bioinformatics is one of the largest data intensive sciences. So it's good to have this data. What do they all have in common? Being this is the biggest things in the world, and this is more the smallest things in the world. They all have in common large amounts of data. Luckily, much of it is stored in relational databases, and we want to query it, okay? So the thing is, how does it work? So I want to emphasize a bit that theoretical research is important, but we also want to see how it works. And we have done this over the last 10 years in very different stages. I started in a bank where I had a real problem, and I teamed up with a few colleagues and we did it. Then at some point, we worked with the bioinformatics guys in Lausanne in Switzerland. They had these large cancer databases. Then we said there was a Zurich startup that actually looked at our papers at some point, printed them out, built a company around it. So they are still doing very well. They are a bit ahead to what we had then. Of course. And then afterwards we said, why can't we not do it even on a larger scale? And then we started a few years ago on this European Union project, where we had people from Greece, then the Max Planck Institute, these were the astrophysicists. The funny thing is when we did the project, we got the Nobel Prize for doing this. Not exactly our group, but the bigger group. So we're very happy that we could say we have this on board. And the Fraunhofer, compression and so on. And basically, let's say here we said, let's do on the European Union scale, let's see what we can solve there, okay? And then we said, okay, let's take this one. We had 3 different databases, astrophysics, cancer research, and some policy making. This is basically a database where the European Union collects all the research grants, all the projects over the history of European Union projects. So this is quite big, and some policymakers want to use it to figure out, Italy has some strong AI research. How does it compare to Zurich or to London and so on? So that's a database. The problem that we had here is if we now want to use these fancy machine learning approaches to these databases, we don't have any training data, because how many people have used astrophysics and have exported natural language SQL or in the cancer research database? So basically, it didn't exist. So this means all these nice ideas that you have when you have benchmarks, they completely fail in the real world where you don't even have a single training data, okay? So that's why the question is, how do we come up with training data? And how would this actually work? And what the Yale guys did before, they said they had 11 PhD students, and they said all of them had to write 10,000 queries. And I find it amazing what they did. We tried in our team here with even doing 100 queries is already hard, and they did 10,000. So then what we did, and this comes out, it will be this year, we said, let's look the experience that we have in our project, turn it into a benchmark, and give it to the world, and let's see how this actually works. And what we did here, we said, the first problem that we have to solve is how we do training data generation. And we said, why can't we generate our own synthetic data and completely, or let's say, semi-automate it? And the idea is that you say, generate a small number of natural language SQL pairs manually. You want something really strong and really good. And if you have astrophysics, it's better to know a little bit about astrophysics, or if it's cancer research, it would also be good to know a little bit. So you cannot just make up any queries, but you need, and that's the important thing is, we had SQL experts and domain experts. These were astrophysicists, medical professionals, bioinformaticians, so those who really understand the domain, and we're sitting together with the other guy. So this means do a few seed queries, then also the test data set where you're evaluating against, this should also be manual. And the rest, we can completely automatically generate. Okay. The question is now, how well did it work? Okay. And this is basically also, I think, you are in the call. So this is work of one of my smart students who is even now in the call, even though it's already midnight in Zurich. So this is the general pipeline, what we're doing. Number one is the seeding phase. Okay, so it says, a typical question is, find all starburst galaxies. So these are extremely interesting galaxies for the astronomers. Then we can write the SQL statement. And then we can do 1, or we can do 10, or we can do 100, as many as you want to write, but you need something. Then out of these queries, find the templates. So what is the abstraction mechanism in there? So in this case, it's AST is the abstract syntax tree. You see it is a select, it needs a table, it needs a column, it has a filter, similar to what we've seen before. And then we say from these ones, we can generate SQL statements. Okay, so generating SQL statements is relatively easy. You can take a database, randomly choose tables and columns. You can write any SQL statement. The question is it semantically meaningful? Okay. So that's why we had here the SQL statements. So once we have these ones, the next step is now translate the SQL statements to natural language. Okay, because giving a SQL statement, we can very easily translate it to natural language. Here, for instance, we have, this is one question, here's another one. Here's, for instance, one question, find the center objects which has nearest neighbor within a neighbor of 2, or find the center of nearest neighbor objects which is smaller than 2. So basically, in this case, we have several translations from this natural language question. And then we use a discriminator phase and say which ones of these translations is the best one. And again, this is to be done completely automatic because this is supposed to be training data generation. And once we have this training data can then be used for training the inverse problem, natural language to SQL. Okay. So you can understand that when you're doing this, using machine learning approach to use training data and then feed another machine learning approach to train on it is kind of a chicken and the egg problem, right? So the question is, how good is this synthetic data that we have generated? And is it actually good enough to take the data and train something else? Okay. So what we did first, we looked at how different, let's say, how does our benchmark differ from the spider benchmark? And let's just focus on the spider benchmark. And if you see here, it has about 186 tables. On average, each database has 3.5 tables. So I think our first year computer science students can do SQL on 3.5 tables. Number of columns, 23. And so one of these databases also has on the order of, what is it? 30 megabytes. So it's small, but there are many small databases. What we have in comparison, we just have 3 different databases. This cancer research has only 6 tables, but in total like 6.1 gigabyte of data, whereas here it's 30 megabytes. And the cancer research has a few more tables, but also on the order of, what is it? Even 12 gigabytes of data. Okay, so it's much more challenging. The question is now, how hard are our queries? Because every time you build a benchmark, if the questions are simple, you can answer them and you always reach a high accuracy. So that's why what is done in this NLP community, or in general for this benchmarks, database community, of course, also participate. You can classify them as easy, medium, hard, and extra hard. And this is from the point of view of a natural language expression, not necessarily from the SQL statement. As a SQL statement, you would say, how many tables does it have? How many joins does it have? How many aggregations and so on? Here it's more from the language side, but we also looked at it from the SQL side. And you will see for these 3 different ones, we have different categories. Okay, so the extra hards are the one that are the most interesting. Yep.
Who makes this determination if a query is easy, medium, hard, or extra hard?
So that's actually nice. Very good question. This is a script. You can take a query, go into a script, and it's automatically evaluated. So this on the spider benchmark, this is already done. So this means everyone has the same evaluation just for this hardness.
So descriptive value is a natural language question.
Exactly, yeah. And then it, depending on how many attributes you have and so on, then it puts them into these categories, okay? So now the first question that we have, how well does the translation work from SQL to natural language? So that's not the problem that we want to solve. That's just the first part, okay? And what we started this some time ago. At this time, we even used GPT-2 and GPT-3 and GPT-0 and so on. And the first one is basically the blue score. And this is some score where you basically compare how much a natural language, a text compares to something else. A higher score is better, and it's not normalized. So it can even go to whatever. It's not between 0 and 10 or 100. So this high score is good. So in this case, the GPT-3 turned out to be quite well. Sentence Bird says Sentence Bird is normalized between 0 and 1. 1 is the best. And here we have like almost 90% accuracy. Okay. And the humans, that's actually the interesting thing. If we look at humans, they got in this case an accuracy of 76%. So this means actually the Sentence Bird is even better in this case. Okay. So basically this shows that natural language to SQL translation or SQL to natural language works quite well, maybe to an accuracy of 80%, but it's maybe good enough. In machine learning, this is typically called the silver standard. Okay, gold standard is 100% correct training data, and silver standard, we know from data, what is data programming, Chris Reed from Stanford kind of coined this. You don't need 100% training data. You can even have sometimes faulty training data. If you have enough, it's still good. Okay. So now the second question is, how meaningful is both the semantic of the SQL, and how well does the natural language and the SQL statements actually correspond? And of course, you cannot go through all of them, because if you generate thousands of these ones, what we said, let's randomly draw a sample of 100 questions and analyze them. So these were humans that did it, and it turned out that the SQL statements are, depending on which field, like astrophysics was 97% correct, and the cancer research like 90%. So what does it mean correct? So for instance, you could maybe then do a SQL statement which is syntactically correct, but semantically it's not meaningful. If you take, for instance, the average number of your the average number of a gene, it doesn't actually make sense, right? Or if you count whatever the average of your shoe size, maybe this might make sense, but sometimes syntactically it's correct, semantically it's not meaningful. Okay. If we look at the semantic correspondence between a natural language and a SQL query, so does it really answer it correctly? Then we see on average on the order of 80%. Yeah.
So for the first question, the semantic meaningfulness of SQL.
Mm-hmm.
So you're just basically taking the SQL generated, and maybe that human expert reviewed this.
Yes.
Say that whether the SQL actually makes sense.
Mm-hmm.
Right. So why I thought, is this more like a natural language to SQL problem? So why not let like the experts review the natural language?
This comes afterwards.
Oh, okay.
This is the first step. Our synthetically generated training data, is it meaningful? And as I said, you can synthetically correct SQL statements. You can very easily do whether semantically correct is something else. And then basically seeing, does a natural language and the SQL correspond? Just for the training data. Okay, yeah.
So being able to like translate arbitrary natural language to SQL, do you need meaningful or semantic, I guess, training data?
Mm-hmm.
Like, is that going to really affect the end result of like how well you're able to translate natural language?
Because the thing is, and we will see this afterwards, all the machine learning algorithms, the better your training data is, the better you can learn. If you, for instance, say, I have many SQL statements that count the average of an ID, it doesn't make sense, or of the primary key, it doesn't make sense. So this means you want meaningful, semantically meaningful queries. So for instance, if a cancer research wants to find out what are the number of cells that are maybe indication that this person has breast cancer or prostate cancer, whatever. So this means you need to build, and then, because depending on this, you have the natural language question. If you generate anything, then of course you can generate anything, but then it's not the context of cancer research, or it's not the context of astrophysics. So it needs to be a meaningful context so that it can learn this is a supernova. Supernova, I know this. Okay, so that's why it's important. Of course, you can generate your training data, everything on your own, but it takes weeks, okay, to build this. Does this answer your question?
Yes, yeah.
Also yours, what you had before? Okay, so this means we could show the training data is not perfect, let's say 80%, but it's maybe good enough, okay? Because either you choose 80% correct training data or you have nothing, okay? So now the question was, how does it work in the real world and how do the systems work? And this slide is a little bit overloaded, but we go slowly through it and we see what's the gist of it. Let's start with this data set. So this is about European Union projects. Here we have the 3 data sets, the projects, the astrophysics and the cancer research. And here we have the different systems. And we started with our system, of course, because this is what we know best. And then we said, we trained this on a small language model. When BERT came out, it had only a few million parameters. And then we said, let's take also some medium-sized language model, and that's T5 from Google or ASMBOB. And that's the interesting thing is, this is from the LN Institute of AI. So you can talk to the guys here. So this is, and then let's also compare it against the latest, greatest large language. Okay? And what it turned out is, let's first look at the zero shot. So take a trained system, don't give any additional training data in there. And then ValueNet performs on the European Union data, 12% accuracy, 100% is the best. So we have 12%. If we add a few more training data, we can go up to 35. So this meaning with the training data that we completely automatically generated, we get an improvement of 23%. Let's look at T5. It performs a bit worse. ASMBOB is also a little bit worse. Okay. Then we said, how is it for astrophysics? And astrophysics, if we start from 0, 8%. If we add the training data, you can get up to 21%. The other ones can go up from 5 to 15% and so on. So 21%, the best system here, the medium size, we look at the other one. It's not so exciting, right? But you can still see with adding training data, 30% improvement. Then with cancer research, we can go without any training data from 13% to 50% from our system. This T5 large was to 65%, so it was even a little bit better than our system. The problem was, if you execute it and you use it for inferencing, you get the answer maybe in a sub-second, and here you have to wait sometimes a minute to generate, to automatically infer the training data, or to infer a natural language question. So this means it's not quite there yet. Okay. So now, how do the big systems work? GPT 3.5 and Llama 2. As you all know, you have to pay for this, and Switzerland has a few banks, but still, also you don't want to spend all your money on just training data. So we use this, let's say, budget efficient. And when we look, how does GPT perform here? Zero shot, 57% on the European Union data. Then you add more shots, it doesn't really change too much. It's still 57%. Llama from Meta is not really competitive, so 18%. Then we looked at astrophysics, which is the hardest problem. Zero shot, GPT-5, 29%, 5 shot, 33%. So with a few shots, you get a little bit more, but 33% doesn't mean it's solved. On the cancer research, we can see also on the order of 50%. And if you look, it's not much different to our smaller system. The important thing is this is 175 billion parameters. This has on the order of 100 million. So I think this one has more than 100 million times more parameters, and it performs equally, more or less similar. Why? Because in our system, we built a pre-processing and post-processing, so we made it a little bit smarter so that it understands a bit astrophysics and a bit cancer research. But the main takeaway message here is text to SQL is far from being solved. Okay, because if you look here, 50% is not what we have. Something which I don't have on the slide here. Once we've finished this, we did a project with the Swiss Federal Institute of Statistics, and they saw what we have done and said, great, we also want it. And then we also evaluated this. And at some point, we have even more complicated data. We have it in German and in English, and French and Italian should come at some point. But they wanted to have 90% or 95%. So, and even if even the best systems don't even achieve 50%. So we see for the actual people who want to use it, it's not so good. For the researchers, it's great. We still have a few years, hopefully, to work on this problem. So it's not a solved problem. It's really a hard problem. Okay. If you want to play with it, we have a leaderboard. It's supposed to be coming out soon. Kate, one of my students, she's finishing up her PhD. Then we can publish it, so people can try it out and see, take another benchmark from a real world community to see how it actually works.
Maybe we'll go into those details. So can you tell us more, like, so what is causing the kind of, what is the most challenging now to kind of translation? So we know that they're not performing that well. You created this great benchmark, and the benchmark has a lot of these interesting queries. But now we see, okay, the results are, but if you can decompose them into, like, you know, the easily more complex,
yeah,
especially looking at the more complex, what it is about them that makes it difficult.
So first of all, to understand the meaning of a question, and then basically
it's really the meaning that's confusing.
The meaning is confusing.
Tactically it will do something, but it's just not.
Yes. So basically the problem is you need every question you have, or every keyword you have in the question, you need to map to the correct table and columns. And that's already a problem, because if what you ask here is find me everything about Zurich, and you don't say about the company Zurich, it gets confused. Or sometimes what you have in a natural language question, and the attributes and the column names and the table names are very different to what you have, then this is confusing. So it sometimes doesn't find the right tables. Or if the question becomes longer, it may be out of a potential 5-way join, it maybe does 3 things correct, but it misses maybe one table because it doesn't do the join right, or it doesn't find the right attribute. So it's really.
But the main difficulty is in mapping, like, the semantics to the schema.
Yes.
This kind of schema mapping problem, more than given the structure of the question, figuring out how to compose the SQL itself.
Yeah. And to add the right tables and to add the right attributes. And if you have then aggregation queries, find the ones. And if you say, I want, let's say, the shoe size of all the people in Seattle, and then you give maybe a select star, that's not good enough. So if you want shoe size, you basically also have to do the projection and there find the correct attribute. So depending on how happy you are with, how strict you are with your evaluation. So I remember a few years ago, I wrote a blog post on Sigmund record where I also had this, and I remember I only had one comment, and one comment was, yeah, and at this time we didn't use large language models. They said, why don't you just use machine translation? But the problem is, and that's also, if you translate English to French and you have translated it, you have won. If you translate English to a database language and then the schema changes, we have lost. Because, even we have some, even if you, let's say you solve everything about movies, but then you have another movie database that has a complete different schema, it's not clear whether you could still answer the question, because it's biased to one specific schema, some specific attributes in another one. So in the end, it's really a mapping. You can describe the problem quite easy. All the keywords that you have in a natural language, you need to map to the right tables and columns and then fix them together so that you make sure that all the things in the questions are actually answered. Okay. Good. Almost done. Page 42.
I think we started later on the chance that some of us will have meetings at 3:30.
Say it again.
So some of us have meetings at 3:30. So
yeah. Good. So future directions, and now, as you've seen, now everything is about large language models and prompt engineering. So the question is now, if we now use the task, we've seen we're on the average of 50%, 100% is the sky that we want to reach. What is a good prompt engineering strategy? We have seen that if you do a clever post and pre and post processing, this can also help add a bit more database language and so on. So there are still many things to do. Another thing is also, if you have more complex questions, then hallucination suddenly kicks in, that suddenly some queries or some tables are invented that actually don't even exist. That's also quite interesting. So what you can do is decompose a query into some smaller ones and maybe address a sub-problem and then build it up and until you have done the complex one. Also, another thing which is only starts now, most of the thing is in English. There is something now a bit in Chinese, but multilingual data sets, English, German, French, Chinese, Romanian, Polish, even other languages. This is still an open research question. And another one, and maybe this could be interesting for you, Magda, also multimodal. Now we did natural language to SQL, where everything is a relational database, but what we have also text and images and videos, and you want to query them also in this way. So this is slowly coming now. Okay. This wraps it up. We have one thing about query optimization. Maybe we can discuss it with Dan at some point, and something about quantum computing. This is not for now, but I still stick around. And then I wrap up, so this should be on time, landing on the moon. Hopefully the machine, the solar panels come out. So conclusions. I think the problem is extremely interesting. Databases has the SQL is a query language, so why not actually doing it in natural language rather than in SQL? I think it's a nice way of combining databases with another field like natural language processing, machine learning. There's still many open questions, and it's fun to build. And if I could interest someone to continue working on this would be fun. Good, that's it. Merci beaucoup.